We are now going to talk more about functions defined by integrals. I had told you to title this page Notes. The question says, suppose that f has a positive derivative for all values of x and that f of 1 is 0. Which of the following statements must be true of the function g being defined as the area from 0 to x of f of t dt? Now, I believe this is a misprint right here. This should say sketch a possible graph of f. So go ahead and change that on your paper. So let's talk about f. It says f has a positive derivative. That means that the slope is going to be positive. So just think, the simplest graph you can make is a graph of a line. You want a line with a positive slope, and you want f of 1 to be 0. So it has to cross through the point 1, 0. So I need a graph that just has a positive slope. So I'm just going to draw a line, positive slope. F has a positive derivative the whole time. Yes, it does. This is f. All right. Part B says true or false. G is a differentiable function of x. In other words, g has a derivative. Simple words. Does g have a derivative? Well, let's look at this right here. Take the derivative of this g. So g of x, according to the problem, is the area from 0 to x under f. Okay? Can you take the derivative of this? Well, if you write g prime on this side, that means you would write derivative of the integral from 0 to x of f of t dt, and you've seen that before. That is equal to f of x. So, is it true or false? Does g have a derivative? The answer is true because of the second fundamental theorem of calculus. That's the explanation. You can either write this or you can do the work. Okay, true or false? G is also a continuous function. Is G definitely going to be continuous? Now, think back to what we learned in first semester. What is the relationship between being differentiable and being continuous? If a function is differentiable, if it has a derivative everywhere, is it definitely going to be continuous? And the answer is yes. And so you can write that it is true, or circle the word true, and put since g is differentiable, g is also continuous. Now, the reverse is not true. Just because it's continuous does not necessarily mean that it's going to have a derivative everywhere. But if you have a derivative everywhere, you definitely have to be continuous. Moving on to letter D, true or false. The graph of G has a horizontal tangent at 1. And explain. Okay. What do you look at when you're trying to find where horizontal tangents are? Hopefully you remember that horizontal tangent occurs when the derivative equals 0. So since we're talking about g, we want g prime to equal 0. Now, up here, we discovered that g prime is the same as f. So this graph is the same as g prime, because that's f. So it's f and g prime both. So at 1, is g prime 0? Well, yes, it is, because it told us to plot that point. So it's going to have a horizontal tangent if g prime equals 0. So that means that this is true, because g prime of 1 is the same as f of 1, which is 0, and that was given right up here. So basically, if you show that g prime and f are related, because you proved that in part B, and f of 1 is 0, which is said in the given, you've proved it. Okay? Now, true or false, does g have a maximum of 1? So what you have to think of if it has a horizontal tangent, it could be a max or it could be a min. So what we have to look and see is what's happening to G at that point. So what you can do is think about the G prime number line. That's what we usually use to talk about local or relative maxes. Here's 1. This is the graph of G prime. To the left of 1, what sign is the graph? The graph is negative because it's below the x-axis. To the right of 1, the graph is above the x-axis. So then you think, what does G do? Well, if G prime is negative, that means G is decreasing. When G prime is positive, that means that G is increasing. So what does that make? 1. Hopefully you see that that makes 1 a minimum, not a maximum. So this one is false. So what do we write? Well, you can say that G prime, which is equal to F, changes from negative to positive, not positive to negative, at x equals 1. G prime, which is the same as F, changes from negative to positive, not positive to negative at x equals 1. That's why it's not a max. Okay, let's move it up a little. Keep the graph in view. Letter F, true or false? G has a local minimum. Well, I've already done all the work for that. That is a minimum, so this is true. How would you explain that? Use the standard sentence that we always write. Since G prime, which is equal to F, changes from negative to positive at x equals 1, there is a local min, at x equals 1. And you did the work up there. Now, if you could see that on the graph without doing the number line, do you have to do the number line? And the answer is no. Some of you are quick enough to just be able to look at the graph and go, oh, it goes from negative to positive, so it's a min, not a max. Great. You don't have to draw the number line. If you can see it and write the sentence without it, you are more than welcome to do so. Okay. Letter G. True or false? The graph of G has an inflection point at 1. Now, remember that inflection points occur when G double prime changes sign. Okay? Now, I don't know a whole lot about G double prime yet. I do know about G prime, though. To the left of 1, what is this graph doing? Increasing or decreasing? Because we want pluses or minuses up here, so we've got to have increasing and decreasing down here. To the left of 1, it is increasing. To the right of 1, it is also increasing, which means that both of those are plus signs. So, is G double prime a point of if there a point of inflection at 1? The answer is no. So this is false. Because G prime increases all the time, or you can say G prime doesn't change direction. At x equals 1. That's why there is no inflection point. We've done a couple of examples. There was one on the first worksheet. There's one in the notes also that talked about the relationship between points of inflection and G prime. You need to remember that inflection points occur where G double prime changes sign and G prime changes direction. Let me say that again. You want to find an inflection point where G double prime changes sign or G prime changes direction. Finally, letter H, true or false? Does the graph of dg dx cross the x-axis at 1? This is probably the easiest one on the page if you remember what that means. dg dx is the same thing as G prime. So does the graph of G prime cross the x-axis at 1? Yes, that is true. So you could say something to the effect of dg dx is the same thing as G prime of x, which is f of x, and f of 1 is 0. Now, just the fact that it's equal to 0, does that mean it crosses? This is what I wrote last year, and now I'm starting to question myself. Looking at the graph, it's because G prime is always increasing as well. It has to cross. G prime is always increasing. I would add that on there because f of 1 is equal to 0 doesn't necessarily mean that it's going to cross. It could bounce off of there. So you could also say that G prime is always increasing. All right. Give you a minute to copy all that down. We're going to move over to the back and do the last FDBI question. Okay, I'm actually going to use the back of this since that bled through so well. All right. Now we have this function right here, made up of straight lines. Let f be the differentiable function shown in the graph, and let the position s in meters of a particle moving along the x-axis at any time t be given by s of t is equal to the integral from 0 to t of f of x dx. Now, what's happened? The t and the x have changed places. Does that really matter? No, it does not. Okay? But we need to do a little bit of review about how position, because if you glance through velocity and acceleration, we need to review how they're all related to each other. So position is denoted by the letter S. Velocity is denoted by the letter V, which is equal to the derivative of S. And acceleration is equal to the letter A, which is the derivative of V, which is the double derivative of S. Okay, so that's the level of progression. It's like position is the function, velocity is the first derivative, acceleration is the second derivative of S. Okay. Now, the first question says, what is the particle's velocity at time 3? Okay. They gave me the position function right here. To find the velocity function, I'm supposed to take the derivative of this. So over here in the margin, so I have a little room, I'm going to recopy the function. S of t equals the integral from 0 to t of f of x dx. So in order to find velocity, I need to take the derivative of this, which means I'm going to take the derivative of the integral of f of x dx. Now stop for a minute. Make sure you're writing your t's and your x's in the right place. This is d dt because that's a t. The t is up there, the x is inside. So when you clean this up, you're still taking the derivative of an integral, but now the x is turning into a t. So s prime of t is equal to f of t, which means that the velocity is equal to the function that you see. So this is velocity. This is the graph of the velocity. So what is the velocity at time 3? The velocity at 3 is the same as f of 3, which in this case would be the y value, which is 4. And in this case, because it says that it's moving in meters and has seconds, this would be meters per second. All right, part B. Is the acceleration of the particle at time 4 positive or negative, and justify? All right. Acceleration is the second derivative. So let's review here. The second derivative of s is equal to the derivative of v, which gives you acceleration. Agreed? That's what we wrote up here. So what is the acceleration in terms of f? Well, since f and v are the same thing, the acceleration will be the derivative of f. So we're talking about the slope on this graph. So at time 4, is the slope of f positive or negative? Well, right here at 4, that looks like a negative slope to me. So f prime of 4 is less than 0. It's got a negative slope. And what would be the justification? Because, remember, it has to be about f, because that's what you're graphing here. F is what? It is decreasing. At t equals 4. Okay. So once again, because f and v are the same thing, since acceleration is the derivative of velocity, it's also the derivative of f. We're looking at the slope on this graph. And the slope at 4 is negative because the graph is going down. All right, letter C. What is the particle's position at time 5? Justify your answer. Okay. When they say justify, sometimes it means a sentence, sometimes it means just show some work. Now, because it says position, position, according to this, is the equation itself. So I'm going to write S of 5 equals, and copy down what I see here. This will be the integral from 0 to 5 of f of x dx. So what does that mean? That means the area from 0 all the way up to 5. So we're talking about this little triangle here and the big one up here. Quickly calculate what the area of this is and think for a minute, will it be positive or negative? And hopefully you see that since we're starting at 0, with some of you I started walking around and showing that if you draw a line where your integral starts, it makes it a lot easier to figure out what sign your area is going to be. This area here, the base is 1, the height is 2, and it's half of it, so that means this is negative 1 in there. This area, because you're moving right, is going to be positive. The distance between these two is 4, and the height is 4, so half of 16, that's 8. So the area from 0 up to 5 is going to be negative 1 plus 8, which is 7. And because it's a position and it's measured in meters, this will be meters for an answer. Okay. Part D. When does the particle pass through the origin? And justify. Now, passing through the origin. Think about that for a minute. When you pass through the origin, do you know something's position, its velocity, or its acceleration? And hopefully you know that its position, when you pass through the origin, the position is supposed to be 0. So I'm going to come over here and say S of t is equal to 0 where? I want you to think for a minute. At. Well, hopefully there's one obvious answer. Because remember that S represents the area. I want to know where the area is 0. The total area. Well, I hope that you see that it's going to be at t equals 0. Because if you put a 0 here, the integral from 0 to 0 of f of x dx will equal 0. I'm going to put that in parentheses because that's the justification for that one. And there's one other place on this graph where the area is 0. But I really need to go and find all the area here. So let's see. What's the area of this going to be? This is going to be, this base is 4. That base is 2. You add them up and that's 6. Multiply by the height, that's 12. And take half of it. That's the trapezoid formula. So this will be 6. But is it positive or negative? Well, because it's below the x-axis, it should be negative. Okay. Now, as you go across here, we figured out that up to here is 7. If you go all the way to the end, it's going to be 1, so it's not going to be back down to 0 yet. So there's nothing past 5. There is a point before you get to 5 where the total area is going to be 0. Do you see where it is? It happens to be at 2. Because at 2, the area of this triangle will be 2. Will be 1. The area of this triangle is negative 1, and they will cancel each other out. So the other answer is that t equals 2, because the integral from 0 to 2 of f of x dx is equal to negative 1 plus 1, which is 0. So this particle will pass through the origin at 2 different places, at t equals 0 and t equals 2. Okay. At what time during the first 9 seconds does S have its largest value? Largest value and justify. Okay. Largest, hopefully, when you think about what word in calculus have we talked about that means, hopefully you know it is a maximum. Now, question is, are we talking relative max or absolute max? Since it's looking for the largest value of all, I would assume this is absolute max. Okay? Now we're talking about the S, the absolute maximum of S. Now S, remember, is area. So we want to find out when the maximum area is going to occur. Because it is a absolute, it's going to be a closed interval. What is my interval from? It is from the beginning to the end of the graph, which would be 0 to 9. That's important because on absolutes we use endpoints. So now you need to think, what are the steps you go through to find an absolute max or min? So stop for a second and think about that. If you need to pause the video, do so. You find absolute maxes and mins by setting the derivative of the function you're talking about equal to 0. You find out where the derivative fails, and you look at the endpoints. Where does the derivative equal 0? Now wait a minute. What's the derivative? Is this the derivative, this graph right here? This is the graph of the velocity. Is that the same thing as the derivative of S? Yes, it is. So I want to know, where does this graph equal 0? It equals 0 at t equals 1, t equals 5, and t equals 9. Okay. Does this graph ever fail? Remember that failure of a graph itself means poles, asymptotes, anything like that. And it doesn't fail in this case. Now, have I addressed all of the endpoints? The answer is no. There's one more, t equals 0. Okay, because I'm doing absolute max, this is where we plug them all in, see which one gives us the largest value. So I want to know S of 0, S of 1, S of 5, and S of 9. Hopefully I've already found some of these. I haven't gone back to look yet. Oh yes, I found S of 5. S of 5 is 7. S of 0. Oh yes, I actually know what S of 0 is. It's 0. Because I already did that. 0 to 0 is 0. S of 1. What's the area from 0 to 1? It's negative 1. That's the area under the curve. S of 9. S of 9 is easy to find. It's the area from 0 all the way to 9. You just add up the pieces. Negative 1 plus 8 is 7 plus negative 6 is 1. Okay. Now let's go back and look at the question. It says at what time. So do I want the x-coordinate or the y-coordinate for my answer? I want the x-coordinate. So the largest value is at t equals which one? T equals 5. Largest value was no. It just said at what time does it happen? It happens at 5. Okay. Letter F. I think I'm going to fold the paper, so give me just a second. Glad I discovered this folding paper thing. It really makes a big difference. I'm going to have to unfold it in a minute when we start doing letter G and letter H, mostly letter G. Approximately when is the acceleration 0? Okay, let's go back and think. Acceleration is equal to v prime. Now this is v, and that's the same thing as f prime. Okay? So f prime is talking about the slope, remember? This is the slope of the graph. So this is asking, where is the slope of this graph equal to 0? Well, where's the slope equal to 0? I see a piece down here that looks flat to me. I would say that the acceleration is equal to 0. Acceleration equals 0 on the interval from 6 to 8 because the slope of the graph f is equal to 0. Is that the only point? Now, some of you may be thinking that it's here also because it changes direction there. And the answer, I would say yes, because you really can't have an acceleration fail. So in this case, I would also say it is also at t equals 3 because f changes direction at that point. It's going to have to come to an acceleration of 0 before it changes direction. Okay, letter G. We are revisiting something we have not seen in a long time. When is a particle moving towards the origin and away from the origin? And justify. Okay, this is where we do those little snake graphs. We haven't done one in a while. So I'm going to come over here. I'm going to draw a number line. Now what's going to help me, unfortunately, I now need to open this up. The graph really doesn't help much. What helps more is what I did on letter E, is these position points. Okay? So the positions that I know of are 0, -1, 7, and +1. So -1, 0, +1, and 7. They don't have to be equally spaced. I'll move this up a little bit. Okay? Now, let's figure out where it's going. Okay? At time 0, it's at the origin. So, I'm going to put t equals 0 right there. And at time 1, it's at -1. This is at t equals 1. So that means it's going that way. Okay? Then, at time 5, it's over at 7. So over here, it has to go this way. Time 5, it's here. And then at time 9, it's back at 1. So that's the direction that it goes. Now, there's one more point that I can actually check. It says that it's supposed to pass through the origin at 2. If it's at 1 here and at 5 here, does it make sense that at 2 it would be at the origin again? And the answer is yes, it does. So you can put that point on there as well. Okay, so now I'm going to make a towards column and an away column. Now, what is it doing on the first leg of its journey? It's moving away from the origin. So I would say that's the interval from 0 to 1. Because, why is it moving away? Because the position at 0 is 0, so it starts at 0, and the velocity is negative. It's moving to the left. Okay? Then, now we can't go all the way from 1 to 5, because from 1 to 2 it's going to the origin, then it goes away again. So from 1 to 2 is my first towards. Because it starts its position of 1 is at -1, and the velocity, it's moving to the right, so the velocity is positive. Now I'm going to draw a line under each one of those because I'm going to put in a second answer. From 2 to 5, towards or away. It's going to the right, starting at 0. So this one is moving away. So from 2 to 5, it's moving away because the position at 2 is 0, and the velocity is positive, moving to the right. Is that correct? Yes, it is. Okay. Now, the last leg of it, from 5 to 9, it's moving back towards the origin. Started second-guessing myself there. The position is at 5 is 7, and the velocity is negative because it's moving back to the left. So that's towards the origin. These velocities here, this was what was bothering me. It may have been bothering you too. Does it really matter what the velocity is? No, it matters that you start at 0 and you move in a direction. Because if you start at 0 and you move either left or right, you're moving away from the origin. If you start someplace else, if you start at a negative and your velocity is positive towards the origin, or if you start at a positive and your velocity is negative, then you're moving away from the origin. Okay, that's probably the most complicated one you're going to see. H, once again, the last question is an easy one. On which side of the origin does the particle lie at time 9? Well, you know what? I just drew a graph of where the particle is. At time 9, where are we? We are to the right of the origin. Why? Because the position at 9 is equal to 1. We're to the right of the origin. Okay, hopefully this clears this up. If you don't understand any parts of it, you may want to go back and re-watch. As you see how the notes are progressing on there, you can pretty much fast forward or rewind as you need to.